So what is this overall text processing pipeline that we're going to be dealing with here? So let's take a little bit closer look at this. All right, this pen is on its way out. So that says text processing pipeline. Basically, what we're going to do is you've got a piece of text. So this is something we've grabbed from a document. In our case, we're going to get these from these text documents. Again, it'll be the text that is a combination of the text field, the headline, and the graphic tag. But then we're also going to need to strip out the extra tags in there. So there'll be a bunch of paragraph tags, for example. These paragraph tags are tags that are just like a letter P. And you don't want them, otherwise you're going to have all these tokens with the letter P everywhere. So it's pretty easy to write a little bit of code to strip those tokens out. You can easily Google how to remove HTML tags from text or something, and you can get a way to process and remove them. Anyway, so we're going to take text. It's free of our tags, so we can think of this as just, it's that string, it's got a punctuation and all this sort of stuff in it. Then we're going to send it, we're going to process it with the tokenizer. That's going to produce for us a set of tokens. Okay, so again, this is for us, our tokenizer. Our tokenizer is all about downcasing or use lowercase. And again, we're going to maintain that our strings are strings of alphanumerics. All right, we're not going to try to separate the letters and the numbers if they're touching. Then you can go to a process known as stopword removal. So stopword removal, its idea is to remove common words such as a and the and of, etc. There might be several hundred of these that are typically removed from words. We'll talk about this and whether to do it or not, but it's usually, if it's going to, so take your text, break into tokens, look at those, maybe throw some of them completely away because you didn't like them. Then put it into to stemming, and where we apply, this is a stemmer. We should apply the stemmer to produce stems. All right. So another, this is a notion of conflation. And again, the example I gave before was about run, runs, running, runner. They all have a stem of run. And so we would take a word and say, ooh, can we reduce it to its stem? And that meaning that all those different types, different varieties of that word are conflated down to one single form, the stem of that word. Again, that is a big recall enhancing technique. The idea is to increase the ability to find matches in these documents, because why should plurals, for example, prevent you from finding matches? You know, oh, I'm really interested in buying a new bicycle. Oh, and then this webpage talks about bicycles. We sell bicycles. Well, if we don't fix that plural in that webpage, we're not going to find a match between my bicycle in my query and the bicycles in the document. And so that conflation is necessary if we want to be able to enable that sort of match. All right. And then the final result is this heads off to our indexer. So the thing that's going to build the index for our system. And again, the index is going to, the primary purpose is to speed up the running of the ranking algorithms. All right, so that's the basic pipeline. Let's take a look in more detail at stop word removal. So again, stop word removal, this removing of common frequent words, all these articles, a, of, the, and so forth and so on. What advantages might we have for doing this? Well, it does save some space in the index. So if we throw these things away and we don't bother to put them in the index, we're not going to write them out again. You know, that very clearly is going to save some space. With really big collections, it's always great to save space. We're always we can always be short on space. Likewise, we're often short in space in memory in RAM. In particular, and if we have to bring in structures from the index into memory, and those are large and numerous, that could be problematic for us. So that can be a nice little savings in space, but we're really usually talking about the index. Getting rid of stop words can improve the speed of retrieval. Because we're going to end up never processing these words when they're in a query. Okay, and in particular, we're in the index that we're going to end up building. What we do is we have a single word, and then we record all of the documents that contain that word. And when we do our ranking, we're going to say, oh, the user gave me this word, and we're going to go fetch that list of documents. We're also going to we're going to do that for every word that the user gave us. So if the user types in, you know, the word the as part of their query, we're going to fetch a list of documents that contain the word the. And we're going to consider them as candidates to actually, should we show that document to the user or not as part of our ranking algorithm? Well, almost every English language document contains the word the. So all of a sudden, we end up having to compute a score for basically every document in the collection, which, if the collection is large, could be really problematic for the amount of memory that we have. It could be just super time consuming. Our goal is not to actually have to compute a score for every document in the collection. We'd like to only compute the scores for the documents that are good candidates that the user might find to be relevant. So this has the real potential to speed up retrieval performance for users. Now, that being said, there are algorithms which are smart and wise about, even if you have a word that's highly common, they'll know that it's not very useful. And it may be able to stop processing of such a list of documents based upon that not very useful word earlier than we might expect with a more naive ranking algorithm. So there are techniques to deal with this. We're not going to cover them. So certainly it could very well be nice for us to remove stop words. It'll turn out, though, that the queries that we use in this class don't really suffer from a lot of stop words and issues like that. And so it's not something that we would run into, but it's for a real search engine, absolutely, you're going to have questions about this. All right. All right, what else? So stop word removal can improve the quality of our results if our ranking algorithm that we're using does not deal well. So the ranking algorithm might not actually be able to understand how to properly sort of ignore the stop words. Again, they're so common, but if it doesn't actually handle that properly, it might mess up our ranking. And so documents that we wouldn't normally consider might get pulled up high into the ranking, and the user goes, what are these doing here? And and these are non-relevant documents, and they're going to hurt the precision of the user's experience using the search, and it's going to slow down their ability to find relevant material. So it's quite possible that it can actually improve the quality because the ranking algorithm doesn't need to deal with this concern. Now these are all actually advantages. So here's a disadvantage for stop removal, is that it can hurt queries, which is really, when we say it can hurt queries, it's going to hurt the end user who's trying to find information to help them satisfy their information needs. So this can hurt the queries that require a stop word. Like, what could that be? Well, examples. Classic one from my supervisor, James Allen, was vitamin A. So imagine, A is an article. It's likely to be in every single stop word list because it's so common in the English language. So if we take this query, we tokenize it, we end up with the word vitamin, the letter A. We go, oh, time to remove stop words. Is vitamin a stop word? No. Is A a stop word? Yes. We throw it out. So now all we're left with is the word vitamin. And now the poor user who's trying to find information about vitamin A is forced to wade through all the documents that only mention vitamin. And it's like, well, this is talking about vitamin C. I wanted vitamin A. Why won't that search engine pay attention to me and give me documents about vitamin A? Very frustrating for the user. I mean, I believe there was a band once called the. Yeah, imagine if you're a user and you're trying to find information about the, and stop word removal is turned on, you're not going to be very happy. So what do we really do in practice? Do we remove stop words, not remove stop words? Well, in general, it seems that what we can do, because space for the index and disk space is not really that big of an issue. We have such large storage space on hard drives now. So in general, we leave stop words in the index but remove them as appropriate from the query. So, how in the world are we going to figure out that we need to remove A from this, the letter A from this query, but not from the query vitamin A? I don't know what to say about that, but we can, if we do keep them in the index, we can then allow the user to require a stop word. So the user could certainly be like, no, don't remove this word from my query, use it. And then we're like, okay. And we use it and we help the user find what they're looking for. Sure, the retrieval might be a little bit slower, but that is way, way, way better to the user than you've produced garbage results for me. This puts the burden onto the user. But I mean, if it can be made clear, oh, we've removed this word to include it, click here. Oh, okay, I want that form of the query. Or if it was removed and it's like, yeah, I don't care if you removed that word. And what do you mean? Like, all right. If it's easy for the user, maybe it's not that bad of a solution. All right. Now, what about this stemming? Well, there are two big ones that we see in research. Certainly, web search companies have their own proprietary stemmers. I still remember Amit Singhal coming to University of Massachusetts and giving a talk. Oh, this is probably somewhere like 2004, 2005, I don't know. And one of the things he recounted was absolutely that it took Google a very long time to figure out a stemming scheme that they felt was actually good and appropriate. So for example, on the web, we just have huge usage of language and terminology and all sorts of punctuation and stuff. I mean, I even just think about, for example, like back to the tokenization problem. So if you have a language like C++, the early web search engines did what I was saying, had very simple tokenization schemes, and all of a sudden you do a query and you're looking for stuff about C++, and these non-alphanumerics were wiped away, and it turned into the letter C. Okay, great. Now you'll find web pages about, let's say you had some other query terms in here about programming languages or something you're looking for, all about the C programming language, intermixed with ones about C++, but you could never focus in on C++ because of the tokenization scheme. So that web companies, in dealing with stemming, Amit said it was very tricky and it took them a long time to find a scheme that they felt worked really well. For us, we're dealing with these traditional newswire articles for our retrieval situation. Stemming certainly is applicable. It's just some basic language being used in newspapers. All right, it could actually help us to find what we're looking for. And this is thing to keep in mind is that whenever we're building a search engine, the quality of it needs to be measured with regard to actual human usage. Whatever the documents that we're doing might be different than another search engine. The user information needs and the queries that come in will be different. And so we need to be able to evaluate and design our system appropriately for the people that we have using it and the documents that are in it. Nevertheless, stemmers, there's two widely known ones and widely used ones, especially for the research community. One is the Porter stemmer, which has been around a long time. Porter gives these examples that all have the stem connect. So you've got connect, you've got connected, you've got connecting, you've got connection, you've got connections, plural, etc., etc. So all of these have as a stem the word connect. Anyway, so Porter is really big on a mechanism that uses rules on properties, common properties of the English language, and basically the rules often know how to chop off the end of a word in some fashion to result in what will be the stem So one of the problems with it is that it can produce non-words. So you started with a word such as abusing, and it'll get stemmed to a bus. I mean, it's not an English word, so as far as I know. The real stem, you would, of course, should be abuse with an E on the end, but that's not what the Porter stemmer turns it into. So, you know, and you're like, well, who cares? This is just the internal representations, the index terms for the document. Well, there are times in which we want to be able to show things about the way the algorithms are working to the user. We might want to, there's all sorts of things. We might want to there are these things with query expansion and similarities, this and that. We might end up being like, oh yeah, I want to use, find the most important words in a document and show that to the user. And our representation, if we've used Porter stemming, produces all sorts of non-words that we don't want to show the user. So that's a downside. From using it, and does it help retrieval or not, Porter stemmer often works really quite well. It's actually quite aggressive, so there's a lot of conflation at hand. In general, it works quite well. The other commonly used stemmer is the Crowbit stemmer. Both of these are named after their creators. And the big thing about the Crowbit stemmer is that it uses an English language dictionary to only accept stems that are words. So it has a bunch of internal rules like Porter does on how to stem. And when it says, oh, I'm going to try to make a stem via this set of rules, it then produces a stem and checks the dictionary. And the dictionary goes, no, that's not a word. Oh, okay, well, I'll apply some other rules to stem it. Did I get a word now? Oh, you did. Okay, that's the stem I'm going to use then. So it works very hard to try to keep them as English language words. Now, what we're going to have tokenization that has alphanumerics in it. What does Crowbit say about a word that is a combination of letters and numbers? My guess is it's like, I don't know what to do with it. Maybe it doesn't touch it at all. So these are things, all of these parts that we put together, they're all interacting. So we start with this huge amount of data, with all these documents. We start turning it into all these words, and we have all these processing steps. They're all interacting with each other. This is a very complex system, especially because of the amount and the variety of the data to actually optimize and improve. And so it's one of the reasons there's so much research on it. Thankfully, because we can measure quality, we've been able to make lots of progress over the years on this. Some notes about, so stemmers, again, they are a recall enhancing technique. So stemmers one thing to note is that they can conflate very different words. To the same stem, which is something that you might not be thinking about happening. So for example, you could take the word organizer and these will get stemmed to organ. So you're searching for something about an organizer, and instead we're getting documents out about organs, either the musical instrument or, human organs and things like that. And all right, we'll still find the documents that contain the word organizer, because all of those documents will have had those words stemmed to organ, and we'll get those matches as well. But we've just ended up lowering the precision of our results often through this mechanism because we did stem organizer. Okay, so now it's time. Now we've gone through tokenization, stopword removal, looked at stemmers. Let's actually look at this little 2-page paper. It's in Learn. The influence of basic tokenization on biomedical document retrieval. Now, in this paper, they run a set of experiments, and we haven't talked about how to measure quality yet, but they measure retrieval quality with a measure called mean average precision. The measure itself is average precision. The mean part is that they are averaging it over all of the test queries, the test topics in their test collection. And so because it's kind of strange to say average precision, we say mean average precision, or MAP. It's a very old evaluation measure. We will talk about it in much more detail. For now, you just need to know the bigger the number, the better the retrieval quality. It's a measure that works in that manner. Now, they do this. They have 2 collections that they have in this paper. So the focus is on, as the title goes, on biomedical, but they also have a collection, which is a standard news collection, which is going to be very similar to what we do. I think actually our LA Times little collection is a subsample of their larger news collection. So they have this one called the Genomics, which does biomedical search tests. And then we're going to look at news. What I'm going to do right now is start to write up some of the schemes that they have. And they also have 2 retrieval methods. One of them, language modeling, or LM, as abbreviated in the table. And the other one is TF-IDF, and which is, I don't know if they even specify. It's the out-of-the-box one from Lucene. So it's some sort of a cosine similarity type traditional thing. Lucene now actually has gone to BM25, is my understanding. Anyways, which is also TF-IDF-y, but it's more sophisticated than the older versions. That probably was what was in Lucene at the time. So let's focus on the LM numbers, the language modeling numbers. So we'll talk about a tokenization scheme, and then I'm going to give the numbers for their genomics results. Actually, I'm going to need more space. So the scheme, and the numbers for the genomics, and then the news, which is similar to the work that the collection we're going to use. So they start off with their sort of the most simple scheme they call the LL scheme. And the LL scheme is just simply to lowercase letters. And basically, wherever I have a string, so they lowercase the text, and wherever I have a string of letters, that's a token. Anything else is not part of the token, and so we break it up in that fashion. All right, so then they measure this, and they find for genomics that they get a score of 0.3. I'm going to actually only go to 2 significant digits, and for news, 0.17. There's a bad habit in a lot of information retrieval papers where they'll report these measures out for 4 significant figures, and that's ridiculous. Now, these authors very nicely use statistical significance testing as well. You can often go out to 3, maybe realistically, but 4, there's no reason for it. 2 significant figures actually kind of goes along with what we will see what ends up being significant or not significant. So this keeps the numbers simpler. Anyway, so this is sort of their baseline. You know, like, can we get any simpler than just, I want a sequence of letters. I'm going to throw away all the numbers. I'm going to throw away anything else that could be of use. In particular, they're concerned in genomics with things, the biomedical type things. There could be Greek letters, all sorts of fancy ways to express, I'm looking for this thing, health-related information. And then the tokenizer, it's like that C++ example. If it's not smart enough, it can just throw away extremely valuable information given by the user. But also, there's a lot more ways that a user might express something that it wouldn't actually match what's in the document. So if someone has some way of like copying and pasting a Greek letter into their query, but in the paper, it's not written as a Greek letter, you know, it's not going to match. Or more likely, the user doesn't type in a Greek letter, they spell it out. So instead of putting in the Greek letter kappa, they spell out kappa, K-A-P-P-A. But in the paper, it doesn't spell out the word kappa. It's because it's a fancy PDF document that's nicely typeset for a journal. It might very well just only have the Greek letter. So how are we supposed to match that? Well, you want your tokenization scheme to come up with a way such that the kappas, however the user presents them and however they're presented in the document, will find each other and be a match rather than a mismatch. Anyways, lowercase letters, trivial. These are our baseline scores with the language modeling methods in that way. Then, oh, well, I don't know why they called that was the baseline, but then they're like, well, let's just do letters only. Let's not lowercase them. So this is not lowercase, okay? So we don't change, we keep things case sensitive, and you know, this hurts performance, but it does not hurt it at a significant level. So it reduces it, but they report these aren't significant reductions. In other words, over their test set, this could just be statistical noise, so to speak. Anyways, so it seems to be better to downcase. Maybe there's something there. Then they look at, they call this LLD. This is where they, this is basically our tokenizer. Okay, so this is, we're going to lowercase or downcase, and we have letters and digits, and we let them stay together. We don't try to break the letters and numbers apart. So for the genomics, we get a small improvement. Again, not statistically significant. Goes up to 0.33. And then for the news, back up to 0.17. Okay. And you could, you know, there might be some notion that you can start to see why it might be good for genomics, because people are typing in fancy things with letters and numbers. They have examples here, and you can take a look at them in the paper. They're in the table. Their next scheme that they apply is, again, let's just do this, but not lowercase. So not lower, but it is letters and digits. All right, then this guy ends up at 0.29. Seems, again, the not lowercasing it is hurting things. All right. Then they have some other schemes. I'm going to skip over them. Okay, so let's look at LLP. So this is LL plus Porter stemming. So we're going to use only letters. They're going to be lowercased, and then we're going to send those tokens into the Porter stemmer, and we're going to see what we get back out. For genomics, this takes us back up to 0.33, but it's still not statistically significant improvement. And for language modeling, we're back up to 0.17. We still haven't done anything. So they're reporting here that if your base scheme is just to use the letters to form words or tokens, and then you Porter stem, at least on their news collection, there's no improvement to using stemming. Okay, same thing with genomics. There's no proof here that stemming is of any value or usage to that. Does it mean it's of no use? Well, depends on whether or not mean average precision is the right measure for our system and so forth. It depends upon whether, are the queries that we're using truly representative of our users? For this experiment, we will assume that yes, we have the right queries and documents and we have the right measure. And so yes, this result for this one experiment says with this base level of tokenization that stemming is not useful to us. Okay, then let's go ahead and we'll do maybe stop words. So we'll use the LL with stop words. So we'll do the LL and then we'll remove stop words. Okay, so this is really this gives us, boom, we're up to 0.35 and it is a statistically significant improvement. Likewise, even though this is 0.17, there is some statistical notion that this is better than this 0.17. I'm just going to skip ahead in the course right now. Just because you've got a tiny improvement and that's statistically significant, is it a significant improvement? The answer is no. It's not a significant improvement to the user. There's no difference effectively from what the user would ever see. Sure, statistically, there might be down in the lower digits some improvement, but trust me, the user would never see this. So we got to be careful about when we analyze and look at results. We'll talk a lot more about this. Then they go and they try some wild schemes. They say, let's just break on non-white space. Or let's make tokens, so the tokens are non-white space. So, by the way, that includes all the punctuation and everything, like it's just anything that's not white space becomes a token and it's all stuck together. So if you have a period at the end of the sentence, that becomes part of the word. That sounds crazy. Yeah, so this drops all the way to 0.17. This is a huge drop in performance. This drops all the way to 0.12. Also a huge drop in performance relative to the baseline. This is like a 27% drop. This is 40 some plus. This is a bad tokenization scheme. Don't do that. This tells us, yeah, we wouldn't want crufty tokens filled with garbage. All right. Then, let's actually lowercase this one. It also doesn't solve that one. Then they create what they call a compound tokenizer, and this one's pretty interesting. They're going to split on white space. So white space are things like spaces and tabs and so forth. They're going to remove non-alphanumeric. Then they apply they've got one, I didn't actually list it, I should have, the SLLD. All right. Now what's interesting about this, I'm going to erase this. what's interesting about this methodology that they come up with is they give an example. It's better to see it in form of an example. So they say, you know, if we have something like B/CD dash CD 28 dash responsive. So this is a very, you know, biomedical type thing. B/CD 28 dash responsive. There could be potentially all sorts of ways that users put that in. What they do is that this gets turned into one token that gets produced is the BCD28 responsive. It basically throws out all of the non-alphanumerics and glues that together. It also then goes in here and then runs a more regular form where it goes, oh, I'm going to split on all this stuff in lowercase. And so then you get a B and a CD and a 28 and a responsive. Okay, and these are all the tokens. So from this one string, we don't just break it into a series of tokens. We also include a token where we've glued it all together. And the nice thing about this is if a user was to type in this sort of thing as a query, great. We've gone and we've produced both of these for the users. But if the user like chooses some other thing where maybe they include some spaces in here, well, the great thing is they include those spaces. We won't get this string, but we will get a lot of these strings down here. So we still have a chance for finding a good match with documents. So it's basically, one of the neat things here is this idea of like, it's not just a string and it's chopped into certain tokens and we throw away stop words and we convert to stems, but you could even envision schemes where we both have the stemmed version and the non-stemmed version, and we index both of them. We keep both of them around so that we can potentially leverage some of the precision and recall enhancing notions of these tokens. So I think this is it's sort of a I create more tokens than we might normally be trying. Almost everything else is recall enhancing. This is a combination of recall and precision enhancing here. And so that is really neat. And then by the way, this then actually, when they do the compound tokenizer for the genomics, it goes up to 0.37. And then for the news, we're up to 0.18. These are rounded up. This is a small statistically significant improvement. Again, whether a user ever noticed that, I don't know. This is quite a big improvement, whole 5 percentage points, so to speak, but it's not statistically significant. So, but then they go, oh, let's go one more step. And of course, this is the piece de resistance of their paper. Is their custom tokenizer. And so they're like, you know, this is the kitchen sink. They're going to throw everything that they've seen that was good in what they've done before. So they're going to take their compound one. They're also going to throw in Porter stemming. They're also going to remove stop words, and so forth and so on. And so you've got stuff here. They even got in here these Greek letter translations they have. So, all right, I throw all this stuff in, and now this does get them up to 0.40. And so this gains them this is a 27% improvement, and it's statistically significant. So compared to the simplistic tokenization schemes, a more sophisticated tokenization scheme, especially designed in their mind for the genomics track, this biomedical track, they're able to get a 27% improvement. Now, it is a really good chance that users over the course of using a search engine repeatedly might actually be like, I really like this search engine more than one that was built with this tokenizer. The ranking algorithm could be the same, all sorts of things could be the same, but it's the tokenizer that has changed because it's able to use index terms which are more meaningful and which enable, from the user's query standpoint, to actually find good matches. So the whole thing together works out. And by the way, for the news, what's really nice about this is their custom tokenizer gets them up to 0.21, which gives them over here a 23% improvement, which is also statistically significant improvement. And again, that's it's 4 percentage points. Maybe it doesn't seem gigantic to you, but imagine if you were Google and this was spread out over, this sort of improvement was spread out over millions of queries a day, and to say that, yeah, boss, we've improved things 23% for the user population. Wow, thank you, that's great. 23%. This is a relative improvement. The 0.4, the 0.04 difference between these would be an absolute improvement. But so the relative improvement is 23%, which is, so that's a really nice improvement. And all they've done is worked on their tokenizer. And so tokenization does matter, and the choices with stemming and stopword removal can matter. And part of what's nice about this is they're showing that small things on their own might not be beneficial, but when we pile them all together, the end result might actually, all of them coming together might result in an improvement that's not very noticeable on their own. So we might very well, if we'd run this experiment with the Porter stemming, go, stemming's no use. But it wasn't until they added in things like the stemmer into their compound one to produce their custom one that they actually got what was a statistically significant improvement, and that's pretty neat. And I think that's really speaks to the notion of why we care about how we actually turn documents into tokens that we're actually going to index. And it all goes back again. It's like the manual way for the humans doing it. It mattered which words the librarian picked. So it matters even how we automatically chop up and choose what to label those documents, which then feed into the algorithms that are going to do the ranking for us. And so it's all interconnected, but these decisions can impact the performance of later algorithms.